So what you're seeing on the screen here is an animation that I took the liberty in animating or scripting on Python in order to depict what receptor activation looks like on the membrane of a cell. And so on the right panel here, what you're seeing is a cursor that is traveling along the 0 x-axis, and then when we apply some voltage or some ligand or whatever, the cursor drops down to a maximum or to a minimum point here at a minimum of 500 picoamps. And that's going to correspond to all of the receptors within our pipette being open. And so if we look at the left panel, the population of open and closed receptors, the open receptors are going to be the pink ones. And you could see as the cursor goes down, goes all the way down to negative 500 picoamps. Again, the negative is relative depending on where your electrode is, where you're measuring. If you're measuring inside the cell or outside the cell, that the negative there is sort of irrelevant. But the idea here again is that the 500 is going to correspond to maximum current passing through the membrane at that time, which means the maximum number or all of the receptors within your pipette are open. Okay, so you see, again, just reiterating one more time, cursor goes all the way down. That when it reaches the peak there, it then begins to bounce up. That bouncing upwards, following that curve, is going to represent the inactivation process of the receptors. And so you could see as the cursor creeps back up to steady state 0, the number of receptors go from open to closed, and we can begin to understand what that curve, the parameters of that curve, how that depicts the number of channels that are open within our pipette. Okay, the steepness of that curve is going to be important to us. That's going to be a constant that we want to understand, and how many time constants are used to construct that curve as well is going to tell us something about the receptors as well. So with that being said, let's go to my whiteboard now and continue with understanding Brugada Syndrome. This is just a really fun animation to look at, and we'll have other animations later in the process. All right, so in the animation we saw before this, we were looking at how the sodium channels open, and we were looking at that in the context of the curve that's produced when you allow sodium to pass through these channels. Okay, the pink things were the open sodium channels, whereas the blue things, the blue dots, were closed sodium channels. We're getting now into kinetics. Okay, we want to understand how we can tie electrophysiological readings to kinetics so that we can understand how these proteins open and close in the context within the face of some ligand or voltage, right? In the case of Brugada syndrome, again, we're looking at voltage, okay? So in the next few videos, we're going to try to mathematically model Brugada syndrome based off of the paper we had mentioned in the last video, okay? We have established so far in the firing process of the cardiac action potentials and the sodium the sodium cardiac action potentials within these channels that carry inward sodium current into the cells. So let's recall the graph here that we had talked about in our first video, where we had sodium slowly leaking into the cell. Okay. These things are called funny channels, by the way. They have this weird property of becoming activated when the cell is hyperpolarized. Okay, so this is a leaky system, right? So it's leaking sodium into the cell, leaking more and more and more and more. Okay, and then then you have this fast depolarization. So slow, and then really fast. That really fast inflow of positive charge is positive calcium, okay, divalent, which is why this is so much faster also, is because you have more charge for one thing that enters the cell. And then you have this really fast depolarization, that's the potassium leaving, and then you have the slow depolarization, which is sodium, again, beginning to enter. Okay, and so that's one round of that's one round of an SA node pump. Okay, we're going to propose that the conductance of these cells follows a Boltzmann distribution. If you don't know what a Boltzmann distribution is, that's okay. We're good. Let's make sense of this equation right here. So G is going to be our conductance. We want to know how many ions are passing through the channel at one time, or within some interval of time. Okay, it could be really fast influx of sodium. It could be really slow. We want to be able to put a number on this. Okay, we're going to normalize it. Okay, when we looked at that animation earlier, if we divide the conductance by the maximum conductance, which was the peak of that amplitude, then this value becomes normalized with respect to that one experiment. Okay. So we have a conductance. We have the max conductance. Okay, and then we have all this in here. So this here is called the half maximal voltage, and this is some slope factor. This slope factor is going to tell us how steep that curve was when we looked at the action potential. Okay, and then this here is the thing that's fundamentally modulated, right? So G, the current, is a function of the voltage or the potential difference across the membrane. So whatever V is, if the potential difference is really small, that's going to change the value of G, right? So you can sort of think of this as, okay, you have a potential across the membrane, and when you change that potential, or when you change the difference across the membrane, so say you tweak the outside by, you add some positive charge or something like that to the outside of the membrane, then you're going to get either really, really fast flow of sodium through your channel or really slow flow of sodium through your channel. Okay, so this thing is going to tell us how much flow through the channel is happening. Okay, and we have this EXP. This EXP is just e to the power of this. We have this 1 plus that. Why do we have this? Well, let's take a look at why we have this, why it's in this form. And we have this -1. Let's see how this. So while the equation seems daunting, we can make sense of this quite easily, actually. So the conductance is a function of the membrane voltage, right? So the membrane voltage across this is V, this is across the membrane. If the difference in the voltage is big, then there's going to be a lot of flow of sodium, very fast flow of sodium through the channel. Okay, then we have V50. This is just a constant. This is something that is intrinsic. This V50, it's intrinsic to the channel itself. Okay, and if we recall it, this is a Boltzmann. This is what's called the Boltzmann distribution. It looks an awful lot like this EXP stuff in here, where we have G max. G max is blue. This is blue here, so this is blue. I've highlighted these just to sort of give us a sense of, this kind of looks like a Boltzmann distribution sort of thing. If you don't know what a Boltzmann distribution is, it's not that big of a deal. We're not really depending that much on this concept of a Boltzmann distribution yet. But the idea here is that the current is a function of the voltage. Okay, I just put this here to sort of show you that it looks like a Boltzmann distribution. When you read the paper, it says it's a Boltzmann distribution. Okay, that doesn't really matter though. The way we're going to make sense of this is we say, okay, suppose V was V50, but suppose the voltage, it's really high and then it goes to half of its value. Okay, it's really high and it goes to half of its value in some amount of time. Okay, half of its value is at V50. Okay, that's the half maximal voltage. So the voltage is really high, goes to half of its value. What happens when that's the case? Well, when V is equal to V50, this can be V50 minus V50. That's going to be 0. Okay, when we have the exponent to the 0th power, that's just going to be 1, right? So we're going to get This again is just the left side of that equation. So we have 1 plus 1 to the minus 1. That's 2 to the minus 1. That's 1 over 2. So this is what we're actually expecting. We want the conductance to reach half of its value when the voltage across the membrane reaches half of its value. So that's why we've structured this equation the way we did. Okay? Similarly, we can define inactivation values, but the inactivation values are going to correspond to the amount of channels that are not conducting. So we inverse the sign of these two guys, okay, and that's going to be the inactivation values, right? So we have activating values, that's going to be G, right? That's going to be the current. You could call it C, you can name it any variable. You just have to remember what it represents, okay? And then we can have I, which is the inactivation. So a conducting current is an activated current. An inactivated current is a closed one, okay? It's not conducting when it's closed. Okay, so we can think of these quantities, I and G, as being the number of closed non-conducting channels and the number of open conducting channels. So the next thing we want to ask ourselves then is there such a thing as an open non-conducting channel? Okay? The answer to this is yes. Okay? You might think, okay, how is that even possible? Well, suppose a channel is open but clogged with a positively charged mutation blocking the channel. We've talked about this already. We've talked about Brugada Syndrome. Right? So Brugada Syndrome is a case in which you have an open, non-conducting channel. Right? You don't get the proper conductance through the pore of the sodium channel. And so because of that, even though it's open, and so because of that, you have this thing going wrong with your heart. Okay? The open non-conductivity, this open non-conductivity represents Brugada syndrome. Okay? So now we get to a fundamental principle in electrophysiology. What is this fundamental principle? The recovery of a channel from the open state to the closed state is mathematically represented as a sum of probability density functions. What does this mean? Let's visualize this to understand what this means. My apologies for the little white bit here, but it doesn't really matter. So suppose we have a closed channel. Closed channel, there's no conductance, there's no sodium passing through the protein, okay? And now suppose we have an open channel, okay? That channel opens, and it allows sodium to pass through, okay? The rate to go from closed to open, how fast, we can ask the question, how fast does the protein take to go from closed to open? What's the rate? Well, we're going to call that beta, okay? And then what's the rate of going from open back to closed? We'll call that alpha, okay? The mean open time is the inverse of the channel closing rate constant, okay? So this is the time it takes is inversely related to its rate, right? So if something's really fast, the denominator here is going to be slow. So if the conversion from open to closed is really fast, this value is going to be really high, right? So if that's really high, 1 divided by a very large number is going to be really small. So the time it takes to go from here to here is really slow. So the rate to go from here to here is really fast. Therefore, the time to get from here to here is really slow. Okay, really low. Same thing here. The time it takes to go from closed to open, well, that's going to be inversely related to that rate again, which is beta. We can make, okay, so that's piece one to this fundamental principle in electrophysiology. So we could take an example of a very simple two-state system. Let's just take this. Suppose we have a system in which the rate of going from open to close is much, much faster than the rate it takes to go from closed to open. In other words, this protein wants to be closed, right? It'll get, once it's open, it closes really fast. But if it's closed, it takes a longer time to open. Okay. So that's the example we're looking at here. And typically this is the case for most proteins. That open state is really, really short-lived. Because you can imagine if it was really long-lasting, then you could get too much ions passing through the cell. If there's too much ions passing through the cell or getting into the cell, that could be DEFCON 1 for the cell. That would be bad news. Right? Cells don't want a huge buttload of positive charge passing through them. Okay, so they're going to have this property where they snap back really quick. Okay, so this is typically what systems are going to look like. Okay. All right. So in this example, we see that the rate of going from closed to open is 100 times slower than the channel going back into the closed state. It takes a lot to open these channels. If we suppose that initially all the channels start closed, then we can define our probability density functions. So let's do this. So we have closed protein, we have open protein. The closed protein and the open protein, the rate here, so the rate to get from closed to open is 100 times smaller than that from going to open to closed. Okay. Well, our probability density function we're going to define as we're going to define this as f of t, okay, is equal to, say, the time. Or actually, no, this is the rate, right? The rate we said was beta, or alpha. So in this case, this is beta, right? So it's going to be beta e to the negative beta times t. And the reason we proposed this is because suppose beta was 0, right? If beta is 0, in other words, the rate here is 0, we're going to be stuck in the closed state. And so the number of closed proteins is just going to be it's just going to be some number, right? So, or sorry, if time was 0, so it's not beta. If time was 0, then what we're going to be left with is just beta number of proteins, right? Beta number of proteins. So this can be thought of as the number of proteins also, but we don't really want to think about it like that. What we want to think about this is a rate, and we define this function. Then we could say, well, if t equals 0 initially, all the proteins are closed. Okay, so initially all the proteins are closed, so we're going to have 10 proteins that are open. That's what that 10 means. Okay. So this is our function, right? So in this specific case, we have f of t equals this guy right here, 10, is that 10, e to the minus 10t, okay. Similarly, we have f of t in the open case, where in the open case we have 1,000 e to the negative 1,000 t. Right, we can graph these. We don't really have to look at this too much in depth, but we can graph these functions. When we graph them, they look like this, right? So initially, in the closed state, we have, say, 200. We start off with 200 proteins, 200 closed proteins, and then there become less and less and less closed proteins over time. Here, less and less open proteins over time. Okay. All right, so we're getting closer to understanding mathematically how we can understand these channels. All right, so the time it takes, again, we said was inversely related to these constants. So we had these equations over here, right? So if t closed is equal to 1 over beta, and this is beta, well, t close, here's beta, is going to be 1 over 10, so it's going to be the time it takes to close is going to be, this is the time it takes to open, right? The time it takes to get from close to open. So the time it takes from close to open is going to be 100 milliseconds. Okay. T open is going to be a lot faster. It's going to be 1 millisecond. because it's just 1 divided by 1,000. So our probability density functions are the f of t functions, so that we have in the above figure. These functions tell us the number of channels that are open at any given time. However, we have not dealt with the sum part of our electrophysiology principle. So we can view this with an animation. Let's go back to that animation and make sense of this now, okay? Okay, we're now looking at the animation again, but we're actually looking at two animations now. One here on the top and the other on the bottom here. And what we're seeing is that the original thing we were looking at the beginning of this video, the original animations at the top, and the new one, that we don't really see that much of a difference in the new one at the bottom here, but there is a difference. If you look at the slope between the two curves, they are a little bit different. The reason for this is because in the bottom one, I have added an additional time constant. We haven't talked about the time constant yet, but now we can sort of begin to make sense of this, right? So in the top panel, this was again our original animation. We are able to see that, or we are able to sort of make sense of this now, where the time constant that we've talked about is going to tell us roughly the slope of that curve. Okay, so when the cursor comes on the 0 axis and then it shoots all the way down to -500, we are then able to see, and then it crawls up. We're then able to, the rate by which it crawls up, or not the rate, but the shape of that curve by which it crawls up, that is dictated by our time constant. Okay, so, and it's the time constant that takes us from the closed to the open state. Okay, we can do the same thing we can create a same curve that takes us from the open to the closed state. Okay, that's just going to change the slope of that diagram, of this graph. Okay, at the bottom here, we're going to go into this a little bit more, going back to the whiteboard. But at the bottom, what I've done here is I've added two time constants so we can see the slope is different. The two times, so the two time constant is going to tell us something about how many closed states there might be. Okay, so let's go back to that and make a little bit of sense of this. Okay, so in that animation, we were able to see now. Okay, so what we were able to see was the initially there was a lot of proteins. All the proteins became activated. Okay, and then over time they began to close, and there was they follow this sort of stochastic behavior, right? Not all of them don't open and then all of them don't close automatically. It's all of them open, and then over time they begin to close. And each one of them has their own kind of unique intrinsic property about themselves, such that each one doesn't open and close all at the same time. Okay, if they did, then you would see the curve look something more like, I'll draw it over here. The curve would look something more like this, right? You do the activation and then no slow recovery after that. Okay. What we've been able to see is that we can generalize this notion of time, of the time it takes to get from one state to the next. So our general probability density function becomes something that looks like this. We say, okay, we have this e here, e to the -10t. The -10 is associated with this rate constant, but now we have these other rate constants. We have this t1c, t2c. What is this? Well, suppose we have two closed systems. Right. This might be open, but not permeable. Right. This could be the constant that tells us something about Brugada Syndrome. Right. This could be the constant, the number that tells us something about Brugada No, I'm spelling this wrong. Brugada Syndrome. I'll put this in quotes, just because we don't want to say Brugada syndrome just boils down to one constant. There's a lot more to it, but we can quantitatively understand it as a constant within these electrophysiological readings. Okay? And so that could be this state right here. Suppose that we could say, I already made this to be closed, but this could be open and just not conducting. It could look something like, I don't have it on this. It could be something open, but it's just not allowing the flow of ions through. Okay. The idea here, again, being that we can actually assign constants now to tell us, okay, we can get from closed state 1 to open state. We can also get from a second closed state to an open state. And we can go the other way, right? We can go from open to this closed, or we can go from open to this closed. What we're starting to do now is we're starting to build kinetic models. Right? When you see a kinetic model, what you'll see is something that looks like, say, closed state. Oh, I don't like it when this happens. We have a closed state, one, maybe you have 3 closed states. You could even have two open states, and when our models might look something like this, right? So you can go between 2 open states. You can go like this. This could be a proposed. This is a proposed. Proposed model of the channel. Okay. And an open, this state here maybe could be associated with a problem in Brugada syndrome, right? This could be closed. This could be open, but not conducting, which is why we're calling it closed. Okay. So if we have a number that we can use to tweak to see what the effects of this are on the overall system, then we can understand how something like Brugada syndrome affects the overall dynamics of the protein. Okay? So in this example, we can now say, okay, suppose now, okay, we have 100, or we have 1,000. Okay, so 1,000 is our constant that take us from closed 1 to open. So that's this 1,000 right here. And then we have 60 to take us from closed 2 to open. All right, so the overall function that takes us from a closed non-conducting state to an open conducting state looks like this. And we have this 0.8 and this 0.2 as factors that tell us what the actual number of proteins is that we're dealing with, right? So this here is, we can call this like A1 and A2, right? My apologies for dogs barking in the background. And so if we have 0.8 and 0.2, those multiply by these constants to give us 100. But this is to say that we have 80% of 1,000 proteins that are initially starting off closed. Okay, or in the closed 1 state. Right, and then this is 20% of the 60 that gets multiplied by the 60, and this tells us the number of proteins that start in the closed 2 state. Okay, so we could tweak these numbers around too and see how they affect the overall system. So what are the numbers that we're tweaking? We want to be able to tweak this and this. Okay, so we can call that beta 1. We can call this beta 2. And we can call the number of channels A1. the number of closed channels in state 2. So we have four constants. We have A1 and A2, and we have beta 1 and beta 2. These things are rates. This thing is populations. Okay? So these are the constants that we want to be able to manipulate, change, and play with to see how we can go from non-conducting closed states, again, my apologies for the dog barking, to an open state, a conducting open state. All right. So we've been talking very general terms here, but I've been talking about Brugada Syndrome, but we're now closer to understanding how we can make sense of Brugada Syndrome, not just conceptually, but also mathematically. So let's remind ourselves what Brugada Syndrome actually is before we continue. Brugada Syndrome is a genetic mutation that resides in the sodium channel voltage-gated ion channels within the heart. This mutation makes it so that the contractility of the heart becomes arrhythmic. Okay? And so far, we have driven deep enough to understand all of the following concepts in biophysics. And not just biophysics, biology and biochemistry as well. The general anatomy of the heart. We talked about that. Proteomics of the sinoatrial node. So we talked about all so many different types of proteins within the sinoatrial node proteins themselves, or the sinoatrial node cells themselves. The action potential patterns of pacemaker cells, cardiac cells, and nerve cells. Okay. Reading and understanding electrocardiograms. Protein topology. A brief introduction to some of the amino acids as well. Electrophysiology recordings, right? We were able to make sense of that. We had an animation for that as well. A mathematical perspective on biology when we were talking about information and function space, and biology being the mapping between those two things. Boltzmann distributions. We didn't talk too much about the Boltzmann distribution, but we introduced its idea and how it helped us relate conductance with voltage. Okay? Ion channel, conductance, and inactivation, right? So conducting is an open channel or an activated channel, whereas non-conducting is an inactivated channel. Probability density function. So the probability density function told us something about the dynamics of our system that we're dealing with when we're talking about the number of channels opening and closing and all that sort of stuff. And then we talked about kinetic models of proteins as well. Kinetic models being you have multiple different closed states and you have some open states. Okay, how we can theorize, we can make a hypothesis about what the model is. The hypothesis being a diagram that looks something like this, right? And then putting it to the test. Right? When you put it to the test, you're changing and modifying variables so that you could see what the effect of those variables are, say, on a computer. And if they produce likely outcomes, okay, that match up with experiments, then you could say, well, the model I predicted, the model I hypothesized is a good model, okay? And we'll continue with that later. This is how learning should be done, in my opinion. I think that we should be able to integrate all of these concepts, and I don't think it's very difficult to teach all these concepts in an integrative way. We have integrated anatomy, physiology, physics, biochemistry, and math to make sense of a disease that you probably have never even heard of, but now you do. And now we're going to continue to dive deep into Brugada Syndrome further. And I also want to remind you why I'm producing these videos. The reason I'm producing these videos is because about 2 weeks ago, a cousin of mine passed away because of this pathophysiology. It was a genetic disease. This is me and him. We went on a fishing trip together, and he was a great friend. He was a great cousin. And I'm making this series because of him. I want to raise awareness of this disease, and I want to bring an integrated and better understanding of biology, biochemistry, biophysics to all of you guys at no cost. Okay. So with that being said, make sure to hit that like and subscribe button, and I'll see you guys in the next video.